Welcome back. We stopped here when figured out the wavelength of a red laser 676 nanometers, and we found that its frequency would be 4.43 times 10 to the 14th 1 over seconds, or seconds to the -1. Okay, so quantum concept and photons. How did Einstein explain the photoelectric effect? And this is where when a metal is heated, it glows red and it emits light. So I have this video linked in Plus Portals. I am not going to play it for you now. I am going to ask that you watch it and take notes on it, and we will come back to it in class. So quantitation of energy. Planck was the first one to look at this, and he said that energy was proportional to frequency, but it wasn't exactly equal to it. So he decided that every time he did a calculation, it was the same number. And so he got to name it after himself, and so H is called Planck's constant, and it's 6.626 times 10 to the -34th joules times seconds. And I would give you that for any calculation that you might need. And so now if we know the frequency, we also can calculate the energy. So calculations I expect you to be able to do right now would be calculate frequency given wavelength, calculate wavelength given frequency, and calculate energy given either wavelength or frequency. We'll practice some of those, don't worry. So Albert Einstein used Planck's quantum theory to explain the photoelectric effect. And so electrons are ejected when light shines on a metal. And not just any frequency of light will work. It has to be the exact right frequency or wavelength. So red light will not cause a potassium to eject an electron, no matter how bright or strong that light is, but very weak yellow light will cause potassium to eject an electron. And this is basically the basics behind solar panels and panels like on a calculator that is solar powered. That's how this works. The photoelectric effect could not be explained by classical mechanics, because in classical mechanics it would be assumed that the element could store up that energy, collect enough to eventually kick out an electron, but it is not true. So, to explain the photoelectric effect, Einstein proposed that light could be described as packets or quanta of energy that behave as if they were particles. So now we know that light works both as a particle and as a wave. So these quanta are called photons. His theory that light behaves as a stream of particles explains the photoelectric effect, as well as many other observations. Light behaves as waves in other situations. We must consider that light has both wave-like and particle-like properties, or it's called the wave-particle duality of light. So here is a picture of the photoelectric effect. If we have a metal and we hit it with red light, nothing happens because the energy or the frequency or the wavelength of that light is not correct to eject an electron. If we change it to a green light, which has a different energy, different frequency, different wavelength, now we can eject an electron. And we can also do the same thing with a different color light. So there's many ones that'll work and a few that don't. So here's your next calculation. What is the energy of a photon of microwave radiation? You don't care, but you do need to know the frequency. And so it's 3.20 times 10 to the 11th seconds to the -1, or 1 over seconds, or hertz. So here's our unknowns, is the energy, we have our frequency, and we know our Planck's constant. And so we can take the frequency times Planck's constant, and that will give us the energy of one photon. Once we calculate that out in our calculator, and we'll do some of these in class so that you can practice it, then it comes out to 2.12 times 10 to the negative 22 joules. So individual photons have very small energies, so the answer does seem reasonable. And you should make sure that energy comes out to a fairly large negative exponent for one photon. What is the frequency of a photon whose energy is 1.166 times 10 to the negative 17th joules? So now we've given you energy and you're going to calculate how to get to frequency. So we're going to solve for E, or we're going to solve for nu, which is nu equals E over h. So energy divided by Planck's constant, and they've got that upside down, is your answer. So, an explanation of atomic spectra. How does the frequency of light emitted by an atom relate to changes of electron energies? When an electron is in its lowest possible energy, the atom is in its ground state, and that means that n is equal to the lowest number possible. When we excite that electron by absorbing energy, we can raise it to a higher level, like 2, 3, 4, 5, or 6. We can keep going. And a quantum of energy in the form of light is emitted when the electron drops back down to a lower energy level. And I'm going to stop on this slide because we're going to need one more video for this unit, or this section. Light emitted by an electron moving from a higher to a lower energy level has a frequency directly proportional to the energy change of that electron. Okay, so I will see you in class. Bye.